My name is Nilesh. I'm going to talk about how we're thinking about evolving our existing platform to incorporate data lineage. Show of hands of anybody who knows Stitch Fix. Awesome, ads are working. Great. So a little bit of information about Stitch Fix. We're a personalized styling service. We style men, women. We have plus sizes that started some time ago. And recently we launched the kids business. We were founded 2011 by our CEO and co-founder, Katrina Lake. And since then we've been working with our clients and styling them, and that's been our sort of business motto. We've employed about 5,800 nationwide. That's probably an earlier figure than what I can remember, but that's the sort of consistent number of our strength at this point. To summarize the business in a nutshell would be algorithms plus humans. So you as a client would come into our system, tell us who you are, tell us what you like in terms of preferences, in terms of what you like, what you dislike, in terms of clothes, in terms of whatever fitting you want. And from that, we want to infer and understand who you are and style you better. So think of it in a simple way of finding the pair of jeans that you want to love and wear pretty much every day. So that's our job, to find you that particular pair of jeans. So the recommendation system understands who you are, takes in your input, gives a recommendation out to a human stylist at the end, who may review it and look at the recommendations that came in front of them and say, oh, you know what, David looks better in this shirt, in this particular jeans, and they may choose the recommended solution or go with something that they want to override with the preferences. And so finally we get you that 5 items that we want to send you, and it comes to your doorstep. You can choose to keep it, you can choose to return it based on what you like. Our goal is to make sure that you keep all the 5 items we send you. A little bit about me. I currently work at Stitch Fix, the data platform team. My particular sub-team works in the compute infrastructure side, so things like our data warehouse, our Spark infrastructure, Presto. I'll talk a little bit about it in my talk, but our team specifically manages the interaction with the data warehouse itself. I used to work for Cloudera not too long ago, where I focused mostly on MapReduce and Spark. I've been a contributor to a few of these projects when I had the time before, and that's a little bit about me. Who here is thinking about data lineage, or at least wants to do something about it, at least? Okay. It is what I like, and I was talking to Rick about it, it's a common problem. I've talked to other people. I've sort of gained their feedback and how they've implemented or their versioning of it. And this is sort of our take on it and how we look at it and how we want to implement it. We're sort of still building this out. This is not fully fledged, built out yet. So we're thinking about how to evolve. And I use this word evolve because we already have this existing data platform that's built out there. It's self-sufficient to data scientists. So how do we sort of think of it as injecting the necessities for data lineage that you need from this data platform? So what I want to cover in this talk is talking about what our ecosystem looks like for our data systems. Talk about data lineage at its basic level. I want to talk about why it's important for us and what kind of challenges do we see. And I'll give you a little bit brief on each of those things. Then I want to talk about the evolution, and this is particularly how we plan to approach the problem, and how do we actually want to change the ecosystem to adjust for data lineage. We have an architecture that we have in mind that might be changing in a few months because we're actively solving different problems in our infrastructure, but at least the approach sort of stays consistent. And I'll leave some time for questions if you have, and certainly we can always meet up in the office hours if you have any other additional questions. Let me start with talking about the data ecosystem that we have. It's a bit of a unique setup. If you look at the bottom, you can see the job execution framework, which is called Flotilla, which is an open source sort of containerized framework. It's an abstraction layer on Amazon ECS, and it allows data scientists to write jobs, write tasks that are scheduled, and you can kick them off with, currently we have different workflow engines. We're experimenting with Airflow. We used to come from the sort of Jenkins world and an inbuilt workflow scheduling. And think about Flotilla being sort of the job running framework for pretty much everything around the ecosystem. Right in the center lies our data warehouse, which is backed by S3, and we have the Hive metastore, particularly to hold all the schema information for the tables. That includes metadata as well, which we can get and insert any other metadata that we need associated with one particular Hive table. I want to start right from the top. If you look at the top and the green bubbles, that's the data ingestion pipeline, which is essentially our Kafka-based system that captures all the event data and writes it into the data warehouse. There's a whole blog that's written out by my colleague who explains a little bit more in detail about how we started thinking about data ingestion and how do we go about building that. And the database snapshots are daily snapshots of Postgres databases from our engineering peers. So think of all the data that's coming into our data warehouse comes from these two sources. And additionally, there are ad hoc sources, of course, but these are the main two larger sources of data that we collect on a daily basis. And everything beyond that happens as a result of transformation or any kind of changes that we want to do to the data after it arrives. And that's mostly run within our team itself. So the uniqueness of the S3 backed with Hive metastore means we can play around with things like Spark and Presto. So going into the Spark side, we have clients and we have readers and writers that are written to talk to Spark. Now, the Spark client mode, or the Spark client way, is more traditional Spark submitting the jobs to an EMR-backed infrastructure. And on the readers and writers side, it's more R and Python-based clients that allow you to talk to Spark. And in this way, we've sort of incorporated Apache Levy to make it a bit more faster to interact with the data warehouse. But in one side, think of the Spark client to be more long-running ETLs, long-running jobs, more production, and the readers and writers could be something smaller, something ad hoc, and something that needs quick results. So that in mind, that is our Spark side. Coming to the bottom, that's our Presto infrastructure. And the nice part is we don't have to worry about writes in terms of Presto, and so like Spark does reads and writes into our data infrastructure. But for Presto, we use that for ad hoc queries. So that means any data scientist who wants to read something quickly, or any business partners who wants to access any sort of data. So we use Looker sometimes to allow business partners understanding a little bit more of the data themselves. So that's interface, and it's backed by a Presto cluster. So we have clients to allow you to run Presto queries in your Flotilla infrastructure or your local machine as well. So coming to data lineage itself, in a traditional sense, and I particularly love this slide because it gets me to present things like this. The lineage would be coming from think of it like a parent-child relation coming way from the top. In the more Harry Potter side of things, it might be more like grandfather, child, grandchild. In the Game of Thrones section, it might be a little bit questionable, but I'm not judging. Think of it as the same fashion, lineage itself, traditionally as you would think about it. And but in the data side, it might be more simpler. So if I have to sort of bring it to a basic explanation, you would think about it as data source getting transformed, written in whatever way between the services, and then getting written to a destination. So how do you see the lineage capturing that we want to do is sort of this journey of data, like coming from the source, what transformed it, what sort of changed it, and then coming down to the destination. Now this can be extended to infinite services and everything that's particular to your organization, but if you bring down to a basic model, this is some way we could explain it, and this is what we want to achieve, at least by understanding the source, the transformation, and the destination itself. Now, why do we care about it, and what do we think is going to be sort of a roadblock and some of the challenges? I want to highlight some of the key terminology that we use. We think of it a resource as Hive tables, which is structured data, and one of the Postgres databases from engineering. So think of those as resources that you have to think about in terms of sources or in terms of something you're accessing. A job in our world is a service-defined batch job, which can perform either a read or write event on one of these resources. An ID would be an identifier for either of these jobs so that you can understand which particular job or which particular application is running. Now, these could be service generated or synthesized on the fly based on what you need. And an event in our world would be a simple read or a write of a resource. So I wanted to highlight these before jumping into what we're talking about. And this is sort of the catch-all for all the resource-oriented changes we need to do, or at least the goals we want to achieve with data lineage. So to begin with, think about it as visibility. Like, why did data scientists need to have visibility on the resources that they're maintaining, particularly if they're sort of if they're cross teams, maintaining different and sharing different resources within the team, then they need to be knowing sort of the dependencies of a resource. And to make it into a single sentence, what is upstream and downstream to a resource? So if a resource is depending on 10 things and it's feeding 10 other different resources, you need to know that. The effects of change is particularly, let's say you move to a different team, which kind of frequently happens between our teams. If there are different projects involved, you're sharing different resources, you're inheriting some different architecture. You end up thinking, oh, what can I do with this particular thing? I need to modify it in a certain way. But the understanding that you have, it's kind of lacking at this point to understand what kind of change and what kind of effects it would have. So think about changing a schema of a resource, and then it breaks 10 ETLs down the stream, and you're wondering in the middle of the night what changed and what happened. So think of it schema changing, data type modifications, and things like that you do without an awareness of what actually happens and what's sort of the repercussions of what you did. The third part is a bit more, sort of tracing long-term understanding of the resource, and it sort of ties back to the initial definition of data lineage. It's understanding how this resource got here, like the source to the destination and the path of what jobs wrote from it, and what actually happened during that journey, and sort of stitching that context of what actually means for lineage for this one particular resource. And I sort of split this out to another section is debugging. Imagine waking up and like, okay, we get paged, but you don't know what to do. Tracing, oh, this particular job failed in this pipeline, but going back and saying, oh, you know what, I don't know which particular job actually failed, but having this sort of graph, or at least having that sort of lineage of where this came from along with the job and what resources it touched, that will help you understand and debug things better. So let's say you have corruption in data or any kind of investigation that you want to do in your pipeline, this would sort of aid that ability that you want to have, at least giving you more control on your own pipeline. And the last part is a little bit more historical, holding information to understand how the trends happened within this resource, how often was it read and written into. So let's say you don't need something, you can look at like sort of the historical information. Oh, we haven't written to that since 2 years. So why do we really need it? We can sort of do some sort of data quality or some sort of cleanup based on that information. This is sort of a pictorial description of what I was just talking about. Think about it, resource C, you're looking at some things that are upstream to it, and then looking at things that are downstream. So having that sort of understanding what is upstream and downstream will be really beneficial for understanding the health of C and any kind of changes you want to do to resource C itself, or even the other resources themselves, which gives you an idea what the dependencies are. Expanding a little bit more on the traceability aspect, in our world, this is pretty much a common pattern that happens. A parent job sort of kicks off a child job, which essentially reads from a couple of different resources, and this could be a little bit more as well, but take a single example of a Spark job reading from a couple of tables and then writing into another table itself. So now you've sort of created this dependency between A and B and then C, and then finally, let's say it extends even further. If C is written or read from another job and then written into D and E, you're looking at more dependencies being added. So that sort of relational dependencies that you need to build is something that we need to interpret out of this job. And sort of at this point, we can't do that in our existing ecosystem. We have all these tools, we have all of this written down, but sort of stitching that contextual information of where this came from is sort of the difficult part we're trying to solve. And understanding where, let's say you read a different resource, but written in a different job, then you lose that context. So if you're written in the same job, how do you understand it happened in the same particular session or same particular job? One of the challenges that are sort of the larger challenge that's why I wanted to highlight this, was more consistency. So think about it in a more diverse world. We still have enough diversity coming from the data ingestion pipeline. You have things to deal with on the Spark side, the Presto side. So different multiple services that are involved within the data ecosystem. And you're trying to change or understand the representation of jobs. Like think about it, the representation of a job is different in Presto and Spark. Maybe some parallels between what it comes from, what the source, or any other information related to a job. But how do you extract some of the points of concern that you need and extract the information that you need out of that particular job or particular run that you already had? And that is something that we're trying to solve at the moment. The nice part about maintenance for our team is we have control about all these clients and all the libraries within it. So there can be changes that can be done within our ecosystem to sort of get past some of this. But the approach we want to take needs to be more simplified, or at least needs to be more streamlined, so that we can understand what exactly we're trying to get out of these services and these job representations. And I want to start talking a little bit about the evolution that we want to do of the existing data ecosystem that you saw earlier. Essentially, I want to describe some of the changes that we're planning to approach this problem. So first and foremost is sort of simplifying the data model of what we're collecting. At the basic level, what we want to know from an event or from a particular job is who owns it. What is the job itself? What ID or any kind of identifier it might be having? What parent job sort of originated that job? And what exact event did it do? Did it read or write a resource? So at the basic level, if we understand this, and we can understand and infer more from just by collecting this and any additional information we might need, we can understand that by experimenting and looking at the data that populates into whatever data store we take to collect this information. And this is sort of a little bit more descriptive of that. A user or owner of a team basically owns the parent job, and they initiate a service which is running a job, and that either reads or writes any resources, and similar for another service within the same parent job. So think about this sort of example of a single parent job that kicks off a bunch of other jobs, and how do you maintain context, and how do you understand some of the ownership and the read and write relevance of each of those jobs within that same particular context of the parent job. One of the easiest thing, or at least the nicest thing we can do, is sort of augment some of the existing clients and existing libraries that we had. So like I mentioned, we have a little bit more control, a little bit more flexibility to do it in the back end. So the goal is to sort of not disrupt any of the data science workflows or any of the stuff that's ongoing in our systems. Things have to pretty much run 24/7, 365. So the idea is to not disrupt some of that workflow and continue doing, while sort of keeping up these things that we have to do to inject extra code to infer lineage. So the one sensitive thing that we might want to take care of right up front is avoiding kind of breaking API changes. If there need to be anything that needs to be changed in sort of an interface that's interacting with a data scientist, you need to be upfront and tell them and communicate well, so that they're prepared to do any kind of changes necessary before you migrate over to the new code. So the sort of policy, a little bit more hardlined, is that you don't change interfaces unless they're actually really important, which is sort of a solid principle engineering-wise, and it's nicer because you don't have any kind of existing burden of maintaining software if we don't do abrupt breaking changes. The other part is to essentially augment the existing tools and libraries, and I'll talk about, in the architectural phase, talk about what we're planning to do in each of them. But the idea is to sort of inject some of this extra information extraction from what we need out of the services, and extract the information that we need from them. The even more nicer part, at least on the Spark side, even on the Presto side, is some of the libraries are pretty back-end, and so the clients only interface with them, so we have a little bit more control and we can change things. And I've done that in the past week. I've changed something and was testing it, so it can be easily done and introduced without a lot of pain, but the effort is, again, to be a little bit more careful and be more idempotent in the workflows that they are. essentially data scientists expect a certain behavior and certain function within their workflows, and keeping that consistent should always be the goal. So even if you're extracting information, making sure that things work the same way is something that is at the core pretty necessary. I want to go over some of the architecture that we thought about how to implement this, and in the data ecosystem that we already have. So we have a lot of Aladdin references in our ecosystem. So I've picked this name for our internal tool for data lineage. Now, whatever it shapes up to be, but Sultan seems like a nice name, and this is the nicest photo I found of the guy, so I keep using it. And this is sort of the idea we have about how to implement something like this. At the basic level, think of it as 4 stages: extracting information, collecting it, doing any kind of ETL work we want to do, and then finally pushing it up to the users who want to gain some of the information out of that sort of relation that we developed. So in the data acquisition phase, think of it as collecting data from your existing tool set, piping it down to an intermediate storage that could be, in our world, a Hive table backed by S3. And then in the third stage, you're thinking about how do we interpret this data? How do we do any kind of relational analogies, understanding what we actually collected? Is it sufficient? Do we need more information to interpret something? Can we get enough contextual information from what we already have, or do we need more things to run? And I'll explain some of that in a little bit, but the understanding, at least what I think about it, is the first 3 stages are going to take pretty much 80% of the time, if not more, because just understanding that we have enough of the data sufficiently to interpret lineage in this context might be bulk of the work, and then pushing it up to data scientists or any kind of end user might be a latter step that can be configured upon later. So the goal is to at least get a clean version of what relations we need to explore, and like at least we come down to the point where we can consistently tell what happens to a resource on a daily basis, or even a dynamic view of it. We can sort of mark it as, oh, we've done enough, and we can experiment further in the later stages. A couple of splits on data acquisition. At least the traditional approach we want to take is the event-driven one. So think of it as firing off an event off of every job or any kind of Spark read and write into our data ingestion pipeline. And we do this for most of our applications. Think of it as a logging store, and we have an HTTP endpoint that enables us. And we already started collecting some of that information in the writing, so we know which table is being written to and which sort of partition has been written to, if it's a partitioned Hive table. And we sort of want to take that same infrastructure and reuse it for this purpose, rather than building something totally new and sort of wasting a lot of resources that may not be needed, but we can always use the infrastructure that we already have. And one of the nice things is we have the S3 sync that allows us to write into the Hive tables. We can specify the schema, and those write into the Hive tables. We had to do a lot. There's a library that sort of converts some of those raw files into Hive, but that's sort of a pipeline that we already have working for us, and we want to reuse that. So again, sort of going back to the approach that the clients will send some of that lineage information over to the data ingestion pipeline. We call it the data highway, and we can collect them into whatever store we want. In this case, would be like a Hive table. On the schedule side, I put this up here because at some point in time, if we fall short of something that we didn't collect out, or we collected and it's not sufficient out of the event-driven side, we're thinking of having something like some ad hoc process running and collecting more information that's missing. So think of it as getting more query information from Presto or any kind of other information that's sort of falls short of what we're collecting at this point. So think of like flotilla logs or any of the container logs that we might need to get more context of who's running the job. Like you can get so much with environment variables, but if we fall short, then there's always this sort of backup or last resort that we need to run, because we're falling short of some parameters in our understanding of the context for data lineage. So it is going to be a bit more harder to maintain. I don't like that approach, but I want to call it out because it might end up being an extra solution that we might need to add. But I hope we don't come to that stage. So look at what our event-driven pipeline looks like. So think about firing an event of read and write, and that goes into our data ingestion pipeline. and we can pipe it down to any other, any Hive table. We have an Elasticsearch that's Elastic that allows us to write there or index it, but for now I think we can do much more with our Hive tables itself. In the second stage, the intermediate data collection, we're again piping it into the Hive tables. So think about going back to the earlier data model that I explained. What we need to collect from a resource is the database name, the table that it's getting written to, and this paradigm called batch ID, which is essentially an epoch timestamp of the version of the data. So what we do is add that batch ID of the epoch timestamp after every write, so that we know that this is the current version of the table or the partition that you wrote into. So if we ever go back or sort of want to go back to an older partition where you missed some data, you can always rewrite and write it into a different batch ID into S3. So that's worked out pretty good for us, and we sort of consistently want to maintain that. On the service side, we want to collect, again, the job, the owner, the parent, and actually the service names. Could be Spark or Presto or any other ad hoc client that's writing out of it. Let's say you're writing from your local system or a Flotilla-backed environment. So understanding that more context within where you're running it from could also be used for understanding where the job came from. I want to dive into what exactly we're thinking about doing in each of these services. On the Presto side, we have some of this implemented already, but we're extracting the information given to us by Presto itself. Like, so some of the query event that gets generated, we added like some custom code and piped it into our data ingestion pipeline, and sort of keep a record of what queries are running and what sort of schema is being touched, and essentially understanding who's writing it. So there's enough contextual information at this point there. But some of the missing pieces is, again, that tying with the parent and child relationship. So we know a Presto query is fired, but we don't know where it came from. Maybe it came from a service, but where did you start that? What is a Flotilla container? Was it your local machine where you're doing some sort of testing in some other machine? So getting that additional parent information helps you tie back and saying, oh, you read it from this. Because what I thought about while thinking about this was, imagine you read something from Presto, but you save it in Spark. You sort of you created a dependency now that we're not aware of. So yes, Presto is good for reading ad hoc, but what if you use that to write into the data warehouse, into a table through Spark? So you sort of miss that link between both of those, that they happen in the same sort of job. So to maintain that, we have to collect sufficient information from both and then sort of tie those things together. There's a lot more work on this side of things on the Spark data lineage. What we're currently doing, and this is sort of, a lot of things are in flight at the moment. We're actively changing how we're executing and deploying Spark jobs. I have a whole different presentation about how our Spark infrastructure works, but we're sort of changing some of that aspect, and we used to rely on particularly the Genie infrastructure coming out of Netflix, which is sort of our redirection layer going into our EMR clusters. And we're sort of changing and taking a different approach and using more heavily in the Flotilla infrastructure that we already have. So think of drivers running in a container and then kicking off executors into our EMR clusters. So it gives us more control. The bootstrapping is not as crazy as it is with Genie. So a lot of improvements in that sort of execution phase that we're going through at this point. The second part is more adding more information. I mentioned we're looking at a lot of the writes at this point, but we're not focused a lot on the reading of data through Spark. So any sort of contextual information of reading is sort of missing in the current world of Spark for us. So we of course, you have our own version of Spark. We fork it out of the open source libraries, but we need to augment some of that to make sure that we collect the relevant information. And the nice thing is, before interfacing with the data warehouse, every Spark job hits our internal library, and that library allows us to read and write data into the data warehouse, along with updating the Hive metastore with the latest information. So think of it as updating the latest location of this table into the one that you just wrote into. So the third part is something I'm more excited about. I recently finished a sort of experimentation of getting Parquet into our mix and sort of getting to a point to move over to Parquet at some point of time. So this sort of experimentation worked, and it's kind of a nicer way to do things. And hopefully in the future we can talk about it more and how we moved into Parquet. But I want to do a bit more testing, be more pragmatic about it, and see how we can approach it in the best way possible, because we have enough we have enough control on those libraries that can allow us to do things. And finally, again, the approach, again, echoing augmenting some of those clients, the Spark clients that we have, and adding more logging or adding more information, like extracting where it's run from. So think of it as running from your local machine. Think of capturing something like a host name or an IP address or something that ties back to a user and say, oh, you know what, the user's local machine ran it, or any kind of environment variables that you can run from the machine that actually executed it. And sort of the third stage is more refinement. And this is more sort of not defined well at this point, because it's more ETL-based extraction, depending on what the data. We're sort of in the phase of the Spark lineage at this point, so implementing that might end up solving some of this and like getting all the information. But the ETL work would come once we collect all that data. So once we have enough of that information, getting that into a cleaner state, into a Postgres table, and finally servicing that to users might be a later stage, but at least the first stage would be to collect all that information. And one of the things I think would be useful to collect more would be aggregated metrics, like over the course of the day, how often was a resource touched, or how often was it read about. And also the main thing would be the resource relationships. So the upstream and downstream relation I mentioned, something that is of paramount importance. We need to get that first, but in addition to that, the aggregated metrics that we can extract from all of this information we have would also be useful to surface some of that into like a trends dashboard or something like that. Like how often was our data infrastructure touched, or how often is our warehouse interacted with. And finally, some of the user interaction portion is what I'm thinking, and this is more abstract at this point. This is some of our early thoughts of how it should look like. It's essentially showing a view of a resource. You want to see what's upstream and downstream to a certain degree. You can go even back further if it's even more if it's even more deeper in the tree, and understand what lies beyond a single edge, and then going downstream and understanding, oh, you know what, I'm breaking 10 of these other things. And this sort of use case is really useful if you're actually doing any kind of hardcore changes on any of the resources, and to understand the dependencies of all of them at once gives you a better idea of doing that change. So let's say you do any kind of breaking changes, you make sure that you go down to the downstream and make sure those ETLs work and those are tested well. If you're changing any kind of aggressive things like data types, let's say you're expecting a string, but it's an int that you've changed it into, you're sort of changing that data model according to your perspective, but you're breaking 10 things down the stream that you don't understand. So at least giving that interface to data scientists would be helpful. And in the more static views, thinking about metrics for the data warehouse, I mentioned that earlier, it's understanding the health of the warehouse and understanding the resources. We already have some of the access logs into S3, and we see whichever objects are kind of being looked at, but that's not sufficient information. It just gives you a sort of gives you a request URL and understanding where it came from, but tying that back to an actual job or anything like that is sort of still harder. In the dynamic views, you're thinking more influx, more sort of intraday changes to a resource. Like, let's say this resource was written 10 times during this day with 10 different partitions. So some tables I've seen are partitioned every 10 minutes. And so that's a lot of data coming in. So tracking that minuscule changes is also important. Oh, let's say we piped in more data from another table. That's something we need to know dynamically on a daily basis. And of course, custom dashboards can always be built beyond what we already provide as the first version or something like that. So that's pretty much it. I wanted to talk about this as our sort of evolving experiment, and sort of how we're thinking of building. In the upcoming months, we're sort of adding more changes to the infrastructure. We're adding Airflow. We're doing all these Spark changes and some of the Presto stuff. So some of this might be inherently solved because of the changes we're doing. But at least on the basic level, we want to implement something like this to infer some of the lineage context we want to gain. So if you're doing a similar problem, I'd love to talk to you and gain your perspective of how you're doing things and what kind of roadblocks you've hit, so that we can understand and do things better. And maybe it's something we're missing totally. that'd be good to know. So thank you for listening, and this is our blog. Feel free to look it up, careers page, and feel free to reach out to me if you have any questions. Thank you.
Hi, maybe I missed it, but I was wondering how you caught every read and write event. Do you have something that intercepts those events, like a daemon of some sort, or?
So in the read side, let's say there's few approaches that we're thinking. We haven't actually done the read side, we've done the write side, but we're thinking like tapping into the input format and the record reader right down below in Spark. Let's say we're actually doing a different approach on the Parquet side, adding a new input format. So if we wrap that up to a different input format, we could always touch the record reader and capture the information from what we're touching. Beyond that, we already have enough clients that, let's say you're grabbing some sort of data frame. You have enough information from the data, from the database name and the table name, and then you can infer from there. And most of the changes around the clients themselves and the ecosystem themselves, like touching the Metastore, touching Spark, would give you some of that references about what job or which particular user is running that. So that's sort of one way we're thinking of inferring some of that.
Yeah, you mentioned a library or a tool that turned the raw files into Hive tables. Was there something in particular that you were using to do that?
That's our in-house tool. Like we're just writing into S3 and just converting it into partitions and then merging it into tables.
You said you were using EC2 abstraction framework or library?
ECS.
No, yeah, but Oh, you're using ECS. Okay, yes. I thought I heard like something like Fratello or something.
Yes, that's our execution framework. That's sort of an abstraction over ECS.
Is that internal or open source?
It is open source. It's called Flotilla OS on GitHub, so you can find it. Yes.
Okay,
Flotilla.
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 Okay.
Think of ships. Yes.
Oh, check it out. Thanks.
Yes, of course.